let's talk comparison tests. So for number 5, I went out of my way to give you something that I was hopeful we would have to use the limit comparison test for. Now, you could do a direct comparison. I'll go ahead and solve this both ways, showing you what that would have looked like. But if you're doing the limit comparison test, that's a good choice for this question because, again, we see an algebraic expression over another algebraic expression, feeling pretty good here. And we just have our n raised to powers in both. So this is going to boil down or have some very strong p-series vibes. So if I have p-series running around, that means that limit's super easy to evaluate in the limit comparison test. And especially because of that -1, when things get a little bit messier in my numerator denominator, I don't necessarily want to do a direct comparison test unless I'm certain that I know something that is going to be larger or smaller depending on what I'm seeing the vibes of. So the thing I was looking for first is that we recognize those vibes. We went, okay, the square root of n over n squared. That's the comparison series, right? Now, again, here's another situation that we got into. A lot of students did a lot of work with the terms of that series and never actually put a summation symbol on it, that big old sigma. And so we'll talk about where they had problems here. So we go, okay, this has the vibes, right? This is the vibes. This is me finding my comparison series. I'm going to get rid of that -1 that's sort of breaking everything for us. So this, I'll be good and keep my summation going. You don't have to have this on every step, right? I mean, you do if you're writing equal signs, but you could have done all this work and then just written their conclusion. But we end up here, and then we end up with our beautiful p-series that we knew was happening, 1 over n to the 3/2. Okay, so again, crucial that we have the series here because we want a comparison series. And crucial that it gets down to one of our known series, in this case a p-series. And so the other piece that a lot of students were missing was, in order to do a comparison test, we need to talk about what's happening with the series, whether it converges or diverges. So we go, okay, this thing here converges, and we need to say why by a p-series with p equal to 3/2, which is larger than 1. So, right, I have the series, I've given the statement, I've said why, and I've given my evidence. All those components that we've talked about previously are in this one thing, this comparison, but this is all based on my vibes. Now, this is basically my b sub n, right? And if I want to, I could be like, okay, b sub n is equal to 1 over n to the 3/2, which we know we could originally write back in that first format, right? Square root of n over n squared. I kind of like that. These are all the same. I'm going to use this version personally when I go to do my limit comparison test. So in the limit comparison test, we do the limit as n approaches infinity. And it doesn't matter which of these two series, which terms, right? The terms of these series we put in the numerator, which one we put in the denominator. So I'm just going to go ahead and leave a sub n as is, my original series. And I'm going to multiply by the reciprocal of the ugly version of b sub n. So here we go, n squared all over the square root of n. Okay, cute. Well, we can see immediately I've got a little bit of work being done. I don't even need you to do that step. If you already see that these have the exact same power, you recognize that this, oops, I lost a -1. You recognize that this is just heading towards 1. And we've discussed, I am completely okay with you not doing 2 L'Hopitals to get here or dividing through by your n squared. As soon as you recognize that we have the same degree on our leading terms for the numerator and denominator, writing out the ratio of those coefficients is completely okay with me. So we've got this limit. Another thing folks failed to do was say, what about this limit is important, right? What does the limit comparison test need? And so writing something along the lines of, hey, this is positive infinite, or R1 ends up between 0 and infinity. Either one of those, I guess I'll do arrows the same direction. One of those two things, something, right, is equal to L, where L is whatever, something to tell me what this limit, what we were looking for. Because a lot of y'all did a great job evaluating the limit, but then didn't say why that one was important, right? It just felt like floating math that had nothing to do with anything. And now we're back to, okay, we have a conclusion. We know because the limit of those terms from our two series, as n approaches infinity, they approach some finite positive number, that the behavior of these two series is going to be the same. And since our original comparison series converged as the P series, we can say the OG series also converged. So again, now it's incredibly important. If I just write the series, we have two series. We have our comparison and our new original. We need to actually write out the OG, right? N squared minus 1 converges. So I've said my conclusion. I need to say what? By the limit comparison test. And then we could be because, and we'd have to write all that stuff out again, but we did all of it. So I'm just going to point my arrow up. Now, if you used any other comparison, this wouldn't have worked, but I didn't see much of that happening around the class. So it was most of us went this correct direction. We did have a couple who tried to do direct comparison here. If you do the direct comparison just to show you, and you did it with this same comparison series, you're trying to tell me that the square root of n over n squared minus 1 is less than the square root of n over n squared. And in this case, we can definitely see that that left side has a smaller denominator than the right side. And so there's no way it's going to end up with a smaller value, right? Dividing by smaller numbers will result in larger numbers, right? But again, you could have also done multiplying through by those denominators to get to here. And then you would have ended up, okay, well, I could divide out that square root of n because we know n is always positive here. And we have n squared is less than n squared minus 1. You can subtract the n squareds, and we end up with 0 is less than negative 1, which is not true. So you could not use a direct comparison. A lot of folks are saying direct comparison and they're not actually checking that these terms are strictly greater than or strictly less than. I guess it doesn't matter about strictly, but they're not checking that condition, right? Okay, the second thing here, if you did want to do direct comparison, I'm pretty sure, I didn't actually try it, so I'll try it right now, that if you want to do a direct comparison, a decent comparison series might be 1 over n squared. This is still a P series that we know converges because our P is equal to 2, which is greater than 1. And now we could show that this is greater. I think we can actually show that if we went to do the square root of n over n squared minus 1, show that that's less than 1 over n squared, but we need to use the direct comparison test, right? It has to be smaller than some known convergent series. Then we do this, square root of n times n squared is less than n squared minus 1. This is not going to be an easy proof, and that's why I wouldn't want to do the direct comparison, but I do feel like it's probably true. I say that because I'm not super confident. I would need to actually do some additional work here to show what's going on. I would need to probably do a proof by induction and be like, well, let's check this for our first term, which is 2. The square root of 2 times 4. Is that less than... Okay, I was just making sure. Is this what I need? Did I write it right? Yeah, I need that to be less than. So we'll see. No, this isn't going to work either. See, y'all? We are in trouble. Yeah, I don't think we could do... Anyways, there's probably some clever direct comparison we can do. But I'm already... That one's not going to work. So this is where, especially when there's additional... Especially when you get really ugly things. I had a couple in the take-home quiz that had giant polynomials divided by other giant polynomials, and for the most part we were trying to do, a lot of us were trying to do direct comparison when it's really, really messy to show mathematically that one has larger or smaller terms than the other when you're using that comparison test.